So the first example which we are going to discuss today is this one. A bullet of mass m moving with velocity capital V strikes the block of mass m whose thickness is A. Find, so what we have to do here? We have to find the resistance of the block suggested supposed to be uniform if the bullet can penetrate through the distance A by 2. If the block is free to move through what distance the bullet penetrates the remaining say. So we have to find the resistance of the block. So how do you solve this problem? So first of all, going to solve this problem, let us see what kind of problem is with us. Suppose this is the bullet and this bullet is going to hit the block. So this is the bullet whose mass is denoted by small m. So this is the mass of the bullet, okay, and this bullet is moving. Say this bullet is moving in this direction, okay, whose velocity is denoted by capital P. Now this bullet will strike or hit the block. So I will take some block here, right? And the mass of this block, I will shade this as block, and see the mass of this block is denoted by capital M. And thickness of the block is denoted by A here. Then we have to find the resistance of the block whenever this bullet hits or strikes this block. This block itself has some resistance, so we have to find that resistance. Okay, so what is that? What we assume that if the bullet can penetrate through the distance A by 2. So this, whenever this bullet strikes this block, so how much distance it will go into that block? So that is this distance, that is half of the thickness, right? Suppose instead of block, if you consider this as a ball, so it is some circle, like, and it has some radius. Thickness means it has some radius. Okay, so whenever such bullet hits the this ball, but this bullet will go into the ball, and that distance is half of this radius. So A by 2, that we are assuming here, right? So if the block is free to move through what distance the bullet penetrates the remaining the same. So this block is allowed to move freely because of the heat of the this bullet. So that is what we are going to assume, and then we have to find the resistance of the block. So we first find the kinetic energy. What is the kinetic energy of a particle? Here particle is bullet, whose mass is small m and velocity is p. So we know that kinetic energy is equal to half into mass into square of the velocity, right? So this is the kinetic energy of a bullet. Let R be the distance, R be the, we denote resistance of the block by this notation R. And when the bullet penetrates through a distance of this a by 2, this half of the thickness, the velocity of bullet becomes 0. So after penetration, that bullet will stop. There is no velocity. And there is no velocity means the velocity is 0. Okay. And therefore, we can find the change in kinetic energy of the bullet. So what is the change in kinetic energy of the bullet? That is nothing but work done by the bullet. So in other words, we are applying the force, right, in this direction on the block against the resistance of this block. So that is nothing but work done by the bullet against the resistance R. And therefore, difference of change in kinetic energy of the bullet is nothing but this. So after when the bullet stops moves, the kinetic energy will be 0, right? And kinetic energy at starting point is half mv square. So this is change in kinetic energy of the bullet, and this is equal to minus R. Why we are taking minus? Because this block is going to oppose the bullet, and therefore we are putting here minus. So here is the action, and this is reaction of the block. So in other words, you are using here Newton's third law of motion, and this is equal to the distance, right, a by 2. And you just find the value of R from this. So this is left hand side is only minus half mv square, and right hand side is minus R a by plus a by R. So minus minus will be plus. Both terms will be positive, and this half vanishes with this half, right? And we write the value of R. So what is finally expression is like this: m small m into v square, which is equal to R into a, capital R, where R is the resistance of the block, right? R, and this is the thickness of the block, A, that we know, right? And to find the value of R, we divide this expression by A, and that means that gives m into square of the velocity divided by A, and this is equal to R. So by this formula, you can find the resistance of the block, right? Now, for example, here if we have a mass of the block is mass of the bullet is, say, we take this mass as, say, 50 gram. Okay. The thickness of the block is, say, per centimeter. Okay. And if whenever this bullet of mass 50 gram moves, it has some velocity, say velocity is 10 meter per second, right? And to know or to find the resistance of the block, you can use this formula. Just put the value of m, p, and a. So m is 50, right? 50, I will do that calculation here. 50 multiplied by 50 multiplied by velocity. Velocity is, say, it is given as 10. So 10 square is 100, right? And divided by A. A is thickness. It is 5, say, and calculate this. So 5 ones are 5. So this is 1 and 0. So 10 multiplied by 100. So that is 1000. So this is the resistance of the block. R is equal to this. Okay. So in this way, we can apply this formula to find the resistance of a block. Now, you can think of such examples. What is the use of this? Such kind of dynamics in our real life situation. Suppose instead of bullet now, you can think of, you take the incidence of say accident, and you instead of bullet you can take this bullet as a car. Okay, right? And this block can be taken as another body or another any vehicle, or it can be anything, right? So what is the resistance? Whenever this car is moving, it has some mass, velocity, then you can find kinetic energy, or yes, by this formula. So what is the resistance of this block? Maybe other vehicle or someone. Okay, but here you have to keep this in mind. This block is fixed. Okay, this is not moving. So whenever sometimes we see that accident took place whenever both the vehicles are moving, right? And we have some accident cases where one vehicle is not moving, but other car hits that another vehicle hits that vehicle which is stopped. Okay, that we see. So in that case, you can apply this formula to know the resistance of that particle or moving car. Okay, so let us see further solution. Now, we have to answer this question second. So when the block is free to move, that is given in the second part of this example, and bullet strikes the block, the bullet and block move as a combined mass. So that bullet together with, see here, that bullet is penetrates in the block. So that block has some different mass, and that mass is the mass is equal to mass of the bullet plus mass of the block. Here mass of the block is denoted by capital M, mass of the bullet is denoted by small m, and therefore the mass, that mass is called combined mass. Okay, with the same velocity phi, then by principle of conservation of linear momentum, we can see that. So here this is combined mass, right? Velocity is this, okay, and this is same as this is the mass of the bullet and it has some velocity. So you see these two, this is by principle of conservation of linear momentum. We have this, and from this you can find the value of v, this small v. See here, this small v is the velocity of the combined body. Combined body, I mean bullet and block, and this v is the velocity of bullet only. Okay, so you simplify this further and you can find the velocity of the combined body. Combined body means bullet and block after penetrating that bullet into the block, right? So this velocity is given by this formula. Now you can find the change in kinetic energies. We know that change in kinetic energy is same as work done, and therefore the change in kinetic energy in earlier case, what is the kinetic energy of a bullet whose mass is m, half mv square, and this is the kinetic energy of a combined mass m. So this is mass into square of the velocity, and this is equal to work done due to the resistance of the block when the bullet penetrates into the block of work. And this is nothing but resistance multiplied by thickness of the block multiplied by through which the bullet penetrates, and therefore we can have half m square as it is. Now we can find the resistance, and that resistance is given by this half. Again, this is the kinetic energy, change in kinetic energy, right? So half into this is the mass of the combined body, then velocity square, and m plus m square, and this is equal to, this is work done. So what is that? Resistance R we have determined. R is equal to m square upon a, and this is the thickness of the block. And you simplify further. So take the product and all those things. So we see that here next expression is, and again solve further. Yes, this is the final calculation. So what we have seen here, if the block is free to move through that, what distance the bullet penetrates the remaining seam. So that distance can be determined by using this formula. Okay. So solve this, because here small m is known, v is known. Yes, we know, we can know, we can find this x stands for distance. Okay. So here through this example, you see the beautiful application of this linear conservation of momentum and all those. Next example. Find the work done by the force F, which is 2xi plus 2yj in a moving particle from this position, whose coordinates are 1 to 2 and 3 to 2. Okay. So we know that work done is given by this integral from P to Q F dr, right? So here we have the vector, this is the actual radius vector, r is equal to xi plus yj. And if you find its derivative, it is simply I dx plus j dy, right? And we know the given force F is 2xi plus 2yj. So we first find this dot product. Okay, so this is vector F, that is given force, and dr vector is this. And using the properties of dot product and, right, dot product of similar vectors. So what is that property? Dot product of similar vectors. Vector I dot vector I, this is equal to, again for another vector j, dot product with itself. So these two products are 1, right? Their value is 1, and I dot j. So this is the similar vector. I dot j, j dot I, the similar vector. So this product, dot product is 0, that we know, and use this here. So what do we get? 2x, right, I into I dx. 2x I have written directly here. So what is the product? 2x I into I dx, right? So I dot I is 1. So therefore, the product of these two terms is 2x dx, right? Then take the product of 2xi with second. So here I dot j is 0. Therefore, this product will, this term will be 0. Plus, now take the product of this with this. So again, j dot I is 0. Therefore, this first term will be 0. and plus second term is take the dot product of these. So j dot j is 1 and therefore you will get 2y 2y dx. Okay, so this is the calculation after using these properties of dot product. So here after this you will have this expression, right? And this is nothing but the derivative of x square plus y square. Derivative of x square plus y square. What is the derivative of x square? It is 2x. And what is the derivative of y square? It is 2y. Okay, okay, no doubt with respect to x. So you can write this is the derivative of x square plus y. And now we can find the work done from point P to Q. So coordinates of point P and Q are given 1, 2, 2, 3. So we can have so d x square plus y. So what is the integration of this 1 into this? So it is nothing but the function itself. So x square plus y square. Put the lower limit and upper limit. So for x is equal to 3 and y is equal to 2. What is the lower upper limit? Upper value is, so put x is equal to 3 and y is equal to 2. So this gives 9 plus 4, right? And put the lower limit. This is 1, square of 1 is 1, square of 2 is 4. So this is 1 plus 4. And you simplify further. This is 13 minus 5. So this is equal to 8. So this is the work done by the force, given force in a moving particle from one point to other point. So in this way, you can have many more examples of this kind. Okay. Next example. A bullet moving at the rate of 3 centimeter per second is fired into a block of wood and penetrates into a thickness of d centimeter. If the block of wood has been d by 2 centimeter, then we have to find the velocity with which the bullet would have emerged through the block, right? So we have to find that velocity. So again, we denote R by capital R is the resistance of the block of the wood. So here, see, in earlier example, we do not know the material of that block, right? But here we have a block of wood. Then the work done by the bullet against this resistance is moving through the distance d is R into. So this is the work done. And this will be the change in kinetic energy. And therefore we can have kinetic energy at starting point, and this is the kinetic energy at the end point. And by principle of linear momentum, you can see that this kinetic energy is equal to R. Now, to find the velocity, we denote velocity by v small letter, and after penetrates through this distance d by 2, we have the change in kinetic energy is equal to work done. So this is half into m. This is the v square minus v square. And you just simplify this further. So you will get this as the result. R dot d upon 2 minus half mv. So where R is the resistance of the block, d is the distance, m is the mass of the bullet, and v is the velocity of bullet, which penetrates in the wooden block. Okay, so whose thickness is d, right? Next, so let us see. Maybe I would be able to finish it within our time. So let us see. So what kind of example you are having here? A uniform string this. Of mass m, whose mass is m, and length 2a, is placed symmetrically over a small smooth page and has particles of masses m and m dash. Okay, so here we have some masses. Those masses are denoted by m and m dash attached to its extremities. So at endpoints, these two pegs whose masses are m and m dash are attached. Extremities means at the endpoints. Yeah, at the endpoints of string, right? String means sakri. So show that when the string runs off, the peg, its velocity is given by this formula. Okay. So let us see how do you obtain this formula. The string ABC, so that string is shown like this in any figure. So this is one of the strings. So other string is denoted like okay. Let ABC is the string whose length is 2a and mass is capital M. Okay. Small m and m dash are the masses attached to the ends of the string A and see the figure. Now we find the weight of the string as BC dash and it is equal to A plus X rho into G. So where rho is the density of string and mass per unit length of the string is given by m upon 2a because it has some length. So in a unit length, the mass of that string is given by m, capital M upon 2a. The weight of the string of length BC dash. We have a string of different length. So we find the weight of that string whose length is BC dash. And it is nothing but A plus X into M upon 2A into G. Because here the unit length is known. And similarly, we can find the weight of the string whose length is A dash. So this is nothing but A minus X. Because why we are taking A plus X and A minus X? Because that gives the position of the point which we are. So it is M upon 2A into G. Now we find the work done in moving the string through a small length dx. So that is given by this. And hence the total work done in moving the mass m down through a distance a and mass m dash up to through a height a so that m dash reaches to the peg. Right? M dash reaches to the peg means that string may be moved along the pulley, and therefore we have this integral minus this integral. Okay, so what is the change? Only this force applied, you can this distance. And if you solve this further, you can apply the properties of integration. You can club because integrands are here first a plus x, second one is a minus x. So a plus x minus a minus x. So that gives this value 2x, right? And just it is simple now. You just integrate this 2x function with respect to x and put finally upper and lower. So that gives mga upon 2, right? So this is the work done in moving the mass, right? So with this example now I will stop here. Next time we discuss another few examples. So one or two examples are there. So I will discuss these examples in the next lecture. So with this I will stop here. Today I will continue.